welcome you to another statistical lecture. In fact, I'm not going to call this lecture, I'm going to call it statistical party. In case you are not enjoying my statistical party, please make sure you reach out. Okay, before I get started today, I quickly want to make an announcement. I've already published my recordings, and I've published, some work examples that the TA is going to walk you through tomorrow. I want you to take whatever the TA is going to be teaching tomorrow very seriously, because they are potential assignment problem. Okay, so that is my announcement number one. Now, let me tell you this. I uploaded only 3 lecture materials for this week. The very first one is probability in a finite sample space, part 1. We're done with that. The second material is the probability in a finite sample space, part 2. We have not finished that. And what we have left in that is what I listed, what you can see. I'm actually going to go over this concept. Then I'm going to go to the third material, and that's called probability model. And you're basically going to see within 15 minutes, we're going to be done with all of that. But let me tell you this, because this course is theory of statistics, for you to be able to understand, I'm basically going to relate to real life practical situation. So let's get started. I want to start with the symmetric difference. Okay, now I'll give you a second. If you really want to understand symmetric difference, you need to first understand relative complement. Yesterday I walked you through what we call relative complement, right? Where I'm trying to say we got 2 non-empty sets, and we are focusing on elements in one and not focusing on the other one. Okay, with that we're doing difference. But when I talk about symmetric, difference, okay, please follow what I do. The reason why I need you to follow what I'm going to be doing is just that, I'm usually sad when I'm grading students and students are getting 0. I'm not happy at all. And that is why I want my student and I to be on the same page in terms of the expectation. Okay? And that's why I'm trying to tell you all this. Now, take a look at this guy. They mean the same. It's a symmetric difference between 2 non-empty sets, X and T. If you take a look at what I wrote on the board, okay, it's an uppercase X, an uppercase T. Okay, that's a set. Okay, when you see a lowercase can never be a set, but a member of a set. So please make sure you take into consideration that. Now, I want you to see what you see in the middle of the S and T. Okay, in some textbook, you're going to see that same notation, and they're also going to see the other notation. They mean the same. Mathematically speaking, what do I actually mean is this. The symmetric difference is just talking about the union of relative complements. You remember yesterday I walked you through relative complement, right? If I have 2 non-empty sets, we're going to talk about relative complement, okay, of X and T. That will be S minus T. Of T and S, that will be T minus X. If I'm now talking about symmetric, our difference now, then I'm talking about the union of 2 relative complements. Now, mathematically speaking, if I want to figure that guy out, I'm actually going to write You see that? That's another way to write it out, which means if you find the relative complement of x and t, s and t, and the relative complement of t and x, then you're going to do the union. Does that make sense? Another way. In your assignment, you know what you're going to see? You are actually going to see a set of x where you have elements, a set of t, you have elements, and we're going to ask you to do all this. Go ahead.
So could you draw like a Venn diagram of it? Because is it just like what isn't in both of them that we're counting?
Oh, you mean whether you can draw a Venn diagram?
Yeah, like just so I can like see what you mean by like what is
exactly.
Yeah.
The essence of Venn diagram make mathematics easy, and that's why if you really want to understand, if you see what we're doing now, we're still talking about relationship between sets, right? But the relationship this time around is a symmetric difference. So which means you can also draw a Venn diagram here. Does that make sense? So whether you draw a Venn diagram or you decide to go whichever way, you're still going to get a result. Okay, go ahead.
No, I was just wondering if you could draw the Venn diagram of this.
Oh, you wonder whether maybe we should draw a Venn diagram for this?
Yeah.
Of course, I will do all of that.
Oh, okay.
I will do all of that. Okay. Is that what you want to ask too? Okay, I will do all of that. Okay, now, as you can see here now, we have x minus t union that. Another way I can rewrite that is this. Take a look at that. If you're given some set, if you find the union of x and t, and you find the intersection of x and t, then perform a relative complement of them. It will still give you the same result. Does that make sense now? Okay, now, if I want to go by, by Venn diagram now that you understand all of that, okay, I'm actually going to do this. Okay, the other time I talked about having x minus t, right? Union t minus x, right? If I have a Venn diagram, okay, and I basically have this guy, and I have this guy, I got x, I got t, okay? Now, what is x minus t? I'm going to shade x minus t. How now? So, just give me 1 second. So, x minus t will be, I'm interested in x only. I'm not interested in t. Take a look at this. You see that? That part is x minus t. Then I want to go to t minus x. The t minus x is going to tell me I'm interested in t. I'm not interested in x. Do you see that now? If you now want to talk about the union now, okay, bringing that together, that's exactly what we have. Any other question? Let me tell you this. A lot of people in the world, students in the world, the students that are struggling with math, they struggle with the math because they don't draw. When you draw in elementary school, the children that don't want to learn before, they will be interested to learn. And that's why I'm advising that you should draw. Does that make sense? Okay, now I want to quickly go into an example. I'm going to quickly go into an example now. Okay, you got a set x. 1, 2, 3, 4, 5, 6. You got a set t. 3, 4, 5, 6, 7, 8. Be careful. If you take a look at this is a listing method. Okay, we can give you in a property method. So you need to understand how to interpret that. Now, if you take a look at this, I want to get a symmetric. Maybe the question asks you this. You see that? The question is asking you to find a symmetric difference between x and t. Now, since you know that you have formula that you're actually going to use, if you want to go by Venn diagram that we did the other time, you can use the Venn diagram. But if you don't want to do that, you can just go directly, since you know x, this is defined as x minus t union t minus x. Now, your question now is, what is x minus t. I want to list out the set. Okay, it belongs to x, does not belong to t. Do you understand? It is only 1 and 2, okay, that belong to x, that doesn't belong to t. Then the next thing you're going to do, what is t minus x? Okay, the t minus x, it belongs to t, but does not belong, to x. That will be 7, 8. Okay, now what am I going to do now to get a symmetric difference? And I'm going to put them together, which is a union. Putting them together now, I'm actually going to have 1, 2, 7, 8. So my final answer now, okay, this guy is now going to be 1, 2, 7, 8. Okay, is there anyone who need clarification on what I just explained right now? This is going to be part of your assignment 1. Okay, please watch out. Okay, now if you want to go by Venn diagram, this is what you can do. If you really want to go by Venn diagram, what you're basically going to do, you needed the one that has to do with this. You needed to use a formula that has to do with this. If you want to go by Venn diagram, I will advise you go with that. Now, what you're going to do when you draw when you actually have what is your XUT, okay? What is the union? It's like combining the two set, but when you combine the two set, no any repetition, okay? So I think I'm going to have like 1 to 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Let me see. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Okay, then you're going to do intersection. What do they actually have in common? I think they have like 3, 4, 5, 6. Okay, they have 3, 4, 5, 6 in common. Now you want to do the relative, for that. Okay, so if you want to do relative for that, it means your XUT minus XNT. Okay, what are the elements that you actually have in S in your T that you don't have is in S intersection T. Okay, and those elements, are the one that we actually, we take a look at this now. Okay, and we take a look at this now. Okay, 3, 4, 5, 6 is just what you're going to subtract from the other one. Okay, so when you do that, I think you're going to get 1, 2, 7, 8. Okay, 1, 2, 7, 8. So you can also represent this by Venn diagram, and it's basically going to be kind of easy for you. Okay, now I just do for 2 sets. Okay, what if I ask you a question for 3 sets? I'm going to give an example now for 3 sets. Okay, I'm going to give one example for 3 sets, and I'm going to go to something else. For 3 sets, if I have this, right, and I have this, and I have this, how many sets do I have? 3, right? Did I write them in a lowercase? No. If you write it in a lowercase, even if you get the result, you'll be marked wrong. A set can never be represented as a lowercase. It has to be an uppercase. Now, maybe the question is asking you this. X minus y minus z. Okay? Now, the x minus y minus z, the elements in x that you cannot find in y and z. Okay? So, I think it's 13 and 15. Check. What are the elements in x that cannot be found in y and z? Okay, I'm done with that. Okay, with that, I think we're already done with that. The next thing we want to talk about now, we want to talk about the properties. We're talking about properties. We want to talk about whether we're going to talk about commutativity, associativity. Okay, now let me tell you this. In terms of commutativity, okay, we're talking about properties now. Okay, this is the same as this. Okay, that's commutativity. You can try that with a set example that I've given you. If they give the same result, okay, that is a commutativity property O. Okay, number two, if we're talking about the associative, okay, you have something like this. This guy also hold. If you try that, just you can assume some set. Okay, so that is basically going to hold. Now, another thing I'm going to tell you this. If you do that with an empty set, it's going to give you that. Try it out. Okay, and if you do it with itself, it's basically going to be empty. Don't forget. Okay, if you do it with itself, it's basically going to be empty. You can also investigate that. Okay, I'm done with the symmetrical difference. I want to go into partitioning of a set. Now, we're going into partitioning of a set. Partitioning of sets. Okay, now we're not talking about partitioning of sets. Of course, the sets that we're talking about have to be a non-empty set. You know, in a partitioning of a set, it's more or less like you are breaking down the set, okay, into separate kind of sets, which I'm going to give you an example now. Okay, if I have this, okay, one of the partition of this is basically, it could be one of the partition, it could be 1 and 3. Another partition, it could be 2 and 3. Another partition, it could be 4, 5, 6. Take a look at that. It's such a way that when you actually, sorry, let me do this so that I don't cause a confusion. It's such a way that when you unify the separate set, it's basically going to give you back the original set. Okay. What is a real life example of partition? Okay. The Vietnam, there's a country called Vietnam. Okay, the Vietnam was partitioned between the North and the South in 1954, according to Geneva Accord, after Indonesia War. But they were unified in 1976, okay, after the Vietnam War. So when you partition, okay, you are actually, why are you partitioning in the first place? Partition, maybe because working with a complicated set, may be kind of difficult to do, and that's why you break it down. You get what I mean? Okay, we do partition all the time. Okay, when you look at your kitchen, you separate the spoons from the plates. You are partitioning. Okay, now that's about that. Then from there, I'm going to go to Cartesian products. Is there any question about partitioning of a set? Any question? Oh, this is your line. Can you see him? Oh, go ahead.
Would the empty set ever be involved in partitioning?
That's a very good question. No. You know, I want you to always think about empty set, being a member, whenever I want to figure out the power of a set. Does that make sense? Okay. Now, the next thing I want to talk about now is the Cartesian product. Please, pay attention. Cartesian product. Okay, there was a French mathematician called René, Descartes. Okay, he actually developed this. Now, let me tell you this. When we talk about Cartesian products, basically, we are just trying to like having the products of set, okay, in an ordered manner. And I'm going to give you, for instance, if I have a non-empty set X, this non-empty set X has members, and I have another non-empty set T. What algebraic sign do you have in the middle? That's a multiplication sign. Okay, it's not X. Does that make sense? That's a multiplication sign. Okay, now we're actually going to do it in a way that we're going to have a pair. You see what I wrote? A lowercase x and y. I need to define that. The lowercase x and y are the elements. X is basically going to come from this guy, and y is going to come from this guy. Does that make sense? So if I'm multiplying two sets, okay, I'm actually going to do that in another manner. Okay, I'm going to give you an example now. Okay, if it's set S 7 and 8, okay, and set C is basically 2, 4, 6. Okay, it doesn't matter. They could have the same number of elements or not. It doesn't matter. Does that make sense? Okay, now I actually want to get this. Okay, so if you want to get this guy down, you don't have 7, 2, okay, 7, 4. Look at the order matter. Please look at the order. Okay, 7, 2, okay, 7, 4, okay, 7, 6. Okay, I've already used 7. Then I'm going to use 8 now. Okay, 8, 2, okay, 8, 4, okay, 8, 6. Look at that. That is a Cartesian product. Okay, is that 7 and 2, 7 and 4, 7 and 6, 8 and 2, 8 and 4, and 8 and 6 is the x, y that I talk about. If you make an attempt, if you want to try whether commutativity work, then the commutativity does not work here. You know why? When you do t times x, the result you're going to have will be different from s times t. Does that make sense to you? Because when you do t times x, the t times s is going to be 2, 7, 2, 8, 4, 7, 4, 8, 6, 7, and 6, 8. That is different from this arrangement. Does that make sense to you? Okay, commutativity does not work when you come to Cartesian product. Go ahead.
Is it true that if you inverse the order for a Cartesian product, that your result will also always be inversed?
Yeah, of course, inversing order is more or less like changing position. You know what I mean? Yeah, that's true. You're changing position. Okay. Now, like I said, commutativity does not work. I just proved that how. Now, what about the associativity? Associativity does not also work. Okay, so what I'm trying to say, you can try that with the example stated. Okay, you can try that with the example stated. Okay, like what I'm trying to say, this times this multiplied by p is not going to give you this times that. You can try that out. Okay, which means the commutativity property breakdown, the associativity property breakdown, but I'm going to tell you what hold. Distributive law hold. I'm going to tell you what is not going to break down. Okay? When you want to talk about, let's look at this. If I have a set A cross B union C, okay? B union C is another set. A is a set. Then you now want to cross them. This is basically going to give you this. A union B cross A union C. This is what we call distributive law. Please take note of what I'm saying. Distributive property hold. The distributive property hold for Cartesian products. Which distributive property am I talking about? Distributive property of union. Take a look at that. It's old. What about distributive property of interception? Let's take a look at that. For the interception, okay, where I'm actually going to have, if I have this guy, the intersection C, okay, basically going to be that intersection that, okay, multiplied by that intersection that. Now, let me tell you now, both, when you're talking about distributive law as regard to Cartesian products, it's old for both union and intersection. But commutativity, associated, they do not hold. The next line of action to finish the material number 2 is the Morgan's law. Before I go into the Morgan's law, any questions, whether in person or online? Are Sophie online? Can you see confirm? Can you see hear me? Sophie online?
Yes, we can hear you.
Thank you so much for confirming that. Is there any other question? Is there any question either in person or online? Like I said, if you don't ask question now, by the time we start a complicated topic, then somebody is going to struggle. These are the basis. That's why I needed to ask question when you get stuck. Okay, now I want to go into the Morgan's law. Now, if I want to talk about the Morgan's law now, before I generalize, I'm basically going to restrict myself to 2 non-empty sets. If I have a set A and I have a set B, and I look at the union between them, and I take the complement of the union, okay, mathematically speaking, okay, this is basically going to give us A complement intersection B complement. Okay, that is number 1 in the Morgan's law. The complement, okay, the complement. If you take a look at this guy now, okay, where we have this guy, we got A, we got B, right? And we're talking about union. The complement of the union is actually outside, right? That is the complement of the union, right? The shaded is a complement of the union. So what I'm telling you automatically now, that is the same as the intersection between the complement of each set. This has been mathematically proved and statistically observed. Okay, now the second law. Okay, which means if you want to verify this, you know what you need to do to verify this. Just get 2 non-empty sets. The very first thing you're going to do, get the union of the 2 sets. After getting the union of the 2 sets, then get a complement. How do you get a complement of a set? Then you need the knowledge of the universal set to get the complement of a set. Because the complement of a set will be other members in the universal set that are not in the set under consideration. Let's have this to now. Now, when you try to get the complement of the union, put the answer in one side. Now, go to the right-hand side of the equation. You have a set A, you have a set B. Get the complement of set A. Get the complement of set B. Then do the intersection between them. They're basically going to give you the same results. That was what the Morgans proved. Okay. Now, this is in the, we're talking about 2 sets. Now, if I were to talk about, the number 2 is, if I have A intersection B complement is the same thing as A complement union B complement. This is the second De Morgan's law. Now the De Morgan's that I'm just stating right now, I'm only putting into consideration 2 non-empty sets. What if I want to generalize? Okay. If I want to generalize, maybe I have like X1, X2, and so on like that. Let's generalize the first one. Okay. Now, when you take a look at the first one, union, and I put Xi, right? Now we take a look at this side and where my I start from 1 probably to N, where I have X1, X2, X3, up to Xn. They are not empty set, and I try to take the complement of that. So when I say the complement of that now, okay, so what I'm actually going to have is going to be this guy, Xi, okay, complement of that. I start from 1 to N. I've generalized. It's a generalization of De Morgan's law for the first one. Take a look at that. We started using notation now. Okay, we started using notation now. Okay, guys. So you're also going to do the same to the other one. Okay, so if I ask you to prove the Morgan's theorem, of course you can prove the Morgan's theorem using Venn diagram, or if you're given data set, then you can also prove it out. Okay, I'm going to use the remaining minute for the last material of the week. If you take a look at the syllabus, the material, the chapters that we're going to cover in the textbook, that textbook is very, very important. In case you don't know, I published that textbook on Canvas. For those of you that may have difficulty in securing the textbook, so please check the Canvas for information. I want to start the last material. Okay, I want to start the last material, and the last material is about probability. I call it probability model. Okay, now let me tell you this. A lot of students struggle with probability. The moment they hear probability, that scares them. You know why they struggle? Because they don't really understand the essence of that in real life. Now, if you take a look at another probability model in this material, you need to understand probability space. Well, I want to walk you through probability measures. Then I also want to walk you through probability model. Now, when you want to learn concept of probability, or when you want to learn anything at all, ask yourself 3 questions. Number 1, why am I learning this? Why am I learning this? If you can provide an answer to that, you're going to be good. Number 2, how do I go about learning this? How do I go about learning this? How do I go about learning this? Do I need a mathematical skill? I know some of you are prerequisite to be able to qualify for this class. Do I need to revise my knowledge of algebra? Do I need to revise my knowledge of calculus? Yes. And number 3, question that you need to ask yourself when you're learning anything, what do society stand to gain from me? You are learning this because of the society, not because of yourself. Okay, now that comes to probability model. Why am I learning probability model? Oh, because we live in a probabilistic world. And we need a model that we can actually apply, and so that we're going to be fine. Because of that, what happened in a probabilistic world? And that was why in the material, I started with random experiments. We perform experiments, okay, random experiments. A random experiment is an experiment that you perform repeatedly and give you different results. And that is why we get worried, because we get different results. If you're an engineer, you use an equipment, right? You are generating values. Even though you are using the same equipment, you're going to give you different values. That's what we mean. And that was why I said, the outcome of a repeated experiment is more than one. Now, because of that, I'm going to say an experiment is random because it has more than one possible outcome. It is not random if the outcome is deterministic. Forget it, we're not in a deterministic world. We live in a world of variation. Because of that, we now need to know how to model our random experiments. What do we need to model our random experiments? Even before we generate an experiment, can we actually figure out a model that will be able to tell us the result we're going to get before we even do it at all? We are so anxious because of that. And that was why I said a random experiment is described or modeled by probability space. I'm going to say that again. A random experiment is described or modeled by probability space. When I say probability space, oh my God, mathematically, what do I mean? In probability space, I got this guy, I got this guy, I got this guy. Oh my God, this is a mathematical definition of probability space. What is it meaning? Oh, omega. If you want to talk about probability, you need to know possibility. Possibility. That is the omega. That is the universal. Then, what is the next one? That look like a calling F. That is a possible outcome. That is the outcome. Some events. Let me say this again. The omega is a possible outcome. Okay, that's like the possible outcome I can get. But calling F is some event. Not all events. Oh, you are preparing for exam, right? What are the possible outcome? Okay, passing, failing. But what do you want? What do you want? You want to pass. Then what is the last one? The last one is the probability measure, which means for every event in a sample space, there exists a probability associated with it. When somebody passes, that person has the probability of passing is high. When somebody fails, the probability of failing is high. For whatever you do, for whatever outcome, for whatever event, there's a probability associated with that. Does that make sense? You know, when you read meaning to all this, math is not difficult. When you read meaning to all of that, you're basically going to be fine. Now, because of that, now I want to go into sample space. You know, the probability. Oh, go ahead.
What exactly is the difference between omega and F here?
If I hear you clearly, what is the difference between omega and F, right? Omega is when you perform random experiment, the possible outcome you could get. The calling F is some event, not necessarily all. But let me tell you, do you know the secret here? You know the secret? The omega F has a larger space than omega, which I'm going to prove for you today. I know what you guys are going to have in mind is maybe the omega should be the one that have a larger space, right? But no, I'll tell you something. I'm going to show you right now. Okay, that's a very good question. Now, if I want to show you that, I'm going to do this. I want us to go into an experiment. You know, I talk about random experiment, right? Let's play with die. Okay, let's play with die. Now, when I talk about die, what is the sample space? When I say sample space, I mean the possible outcome. 1, 2, 3, 4, 5, 6, right? So this is omega. This is the sample space. When I perform experiment, with a die. Okay, now, if I have it like this. This is when I toss a coin once. Sorry, when I toss a die once. When I toss it, maybe 3 times. Okay, let's say for instance, I'm not talking about die anymore. I want to talk about coin, and I toss a coin 3 times. Head, tail, head, tail, head, tail, head, tail, head, tail, head, tail. Of course, I know you've seen this before, the tree diagram, right? And you have head, okay, head, tail, and so on like that until you get to T. These are sample space. If you want to work with probability, you need to first understand your sample space. Okay? We perform experiment. Now, we now want to talk about outcome. You know, somebody asked, what is the difference between outcome and that? Okay? Do you know if I have this guy now, if I perform experiment with a die, right? Okay? And maybe what I'm looking for is even numbers. Then that even numbers will come from the sample space. Oh, 2, 4, 6. Oh, odd numbers. We also come for that. Or less than 4. Or only one tail. Or in the case of the coin, of course, you're going to see that we're actually going to get a lot of that. So that's more or less talking about event. Now, let me now come to your question now. Calling F, right? Calling it. You know the sample space now, right? Possibility, right? We now want to talk about probability. Okay, space. In probability space. Okay, you want to talk about this guy. Give me 1 second. That's a poor diagram. You want to talk about this guy, right? You want to talk about that guy, and I'm going to give you this definition. Number 1. Sample space is lie in that guy. I will prove that to you now. Which means that guy is bigger than the sample space, right? Okay. Now, if sample space lies in that guy, then number 2, okay. If let's say X is set lying in the calling F, okay, lies in a calling F, then the complement of it also lies in a calling F. I'm going to give you an example now. Please follow what I want to do now. Okay, very, very crucial. What I want to do now, okay, is crucial, and I need you to follow that. I want to prove to you how sample space is contained in the calling F. Are you ready? You want to see it? An example is the power of a set. Let's take a look at that. Oh my God, you're going to see something now. Okay, let's take a look at this. Let's say the sample space is actually 1, 2, 3, right? Let's say this is a sample space, right? What is the power of a set? The power of a set is a calling F. Now, the power of a set, the power of this guy here, okay, the power of a set is basically going to be 1, 2, 3. Okay, 1, 2, 3. Then 1, 2, 1, 3. 2, 3. 1, 2, 3. And empty. Now tell me, which one has a good number of elements between the sample space and the calling F and the power of the set? Which one? The cardinality of the sample space is 3, but the cardinality of the power of a set here is 8. And you can see omega is inside the power of a set. Therefore, the example of the calling F is the power of a set. Do you see the difference now? Does anybody see the difference between them now? And that was the reason why I made a statement. I made a statement the other time. I want to go back to the statement I made. I said this guy is in Colin. I've demonstrated that. Let me write my that very well. Okay. And I said if I have a set X, okay, and that set S is in Colin F, okay, then the complement of it is also in Colin F. Let us see. For instance, in the power of a set here, okay, if I only consider 1, 2, and 3, right? What is the complement of 1, 2, 3? The complement is others in the power of a set, right? Okay, so the complement and the one I considered, they are all inside the power of a set. That's what it means. Any question on that? Okay, and that is how that is actually done. Okay, now you understand all of that. Now, how many more minutes? Like 5 more minutes, right? Okay, let me quickly. Okay, now, I'm only going to give you assignment on what I taught you. Okay, and make sure in the lab tomorrow, pay attention, because I want everybody in this class. If the average of this class can be 100%, I'll be the most happiest person on earth. Okay, so now take a look at this. If I toss a coin once, the sample space is this, right? If I now ask you a question, okay, what is it calling F? Can somebody tell me? What am I trying to say? If I give you the sample space to be that, and I say define the calling F, what am I asking you?
It's heads, tails, tails and heads, and then an empty set, yeah?
An empty set, which means I'm actually asking you the power of a set, right?
Yes.
Now, that's good. Set it better to me for a sacred. Okay, so which is going to be this guy? Just like what he said. This, okay, and this. That's exactly what I mean. And when I say cardinality, please watch out. There's a difference between a set and the cardinality of a set. The cardinality is just, take a look at this. When I do this, please pay attention to this. When I say find that, and I say find this, okay? Here the answer is 2. Here the answer is 4. You see the difference? When you see that thing is not an absolute. I know in maths, they also use that as absolute. Here, I don't mean absolute. I mean cardinal, the number of elements that we have in it. Please take notes. Okay, go ahead.
So there wouldn't be tails and heads.
You mean having a tail and another one like tail head?
Yeah, like the tail came up first. Would that be part of it, or?
Oh no, it's not going to be part of it. That's
okay.
A good question. It's not going to be part of it. For instance, if I write that, maybe my sample space was tail first, head for then you're going to have what you said. But I don't know if it's going to be 4.
Okay.
Yeah, that's a good question. This is where I'm going to stop. Okay, the first assignment, like I said, will be released on Sunday. I will be due on Sunday. Sorry, the following Sunday. And when you're going to do it in the lab tomorrow, please, if you can check the canvas right now. What the TA is going to walk you through, I've already published that on Canvas. Please pay attention to that and pay attention to some exercise in the textbook. That way easy. Is there anybody want to ask a question before I go today? Okay, go ahead.
Were you calling the symbol curly F? Is that what, like, if you asked on like the homework, would you ask like what is curly F, or is there like a name for it?
That's a very good question. So you are wondering when I'm going to call that, whether if I want to ask a question, I'm going to say, okay, find calling F, or this. I'm going to say power of a set. Okay, and whatever I wanted to find, I'm going to define that, because you know what, I want us to be on the same page. So okay, so that's a good question. How we have to define that. Yeah, go ahead.
Is there like a specific symbol, like a Greek letter that's used to represent it, or are you just like stylizing an F?
Oh, the symbol that I've used today is the one that we commonly use, like by mathematicians.
Okay.
When you say calling, that that's what they call calling F. It's not F like okay, a F that cough or something like that. That's a calling F. Yeah, that is the notation we use. Okay, and I will also advise that you should also follow all those notations. Okay, but if I want to use a different notation, I will define it. Does that make sense, right? Okay, but I don't want to punish a student for giving out a confusing instruction. You understand what I mean? So, okay, that's a good question. Okay, before we go, I've taught you this just beginning the last we've done 1 week. I need you to send me a message. Rate your understanding of this class from 0 to 100. If your understanding is less than 100, include in your message what you need. Maybe you need clarification. Maybe the reason why your understanding is not up to 100% is because you need me to clarify something. I want to hear from you. Send a message to me. Rate your understanding of this week lecture. We're done now, right? Okay. It's only my TA that will walk you through some exercise tomorrow. Like I said, do not hide your feeling. You pay for the service. You deserve to be served better. Have a nice weekend. Others of you online? Is there any? Oh, somebody say 100%. Oh, good. 100%. But you know what? Do not hide your feeling, okay? If there's anybody online, you send me a message. If there is anything that you want me to clarify, okay? Bye for now, everyone.
Thank you so much.